In the previous video, we began our discussion on winds. What we saw was that there are four basic forces that cause the air to accelerate. The first two forces we discussed in the previous video, which were pressure gradient force. That was the force due to differences in pressure. In other words, it's the initial force that causes the air to move in the first place. And we also discussed the Coriolis force, which is an apparent force due to the turning of the Earth. Basically, this is the force that determines the direction the winds will ultimately go. In this video, we'll continue by introducing the other two forces, the centripetal force and friction. The centripetal force is a balance between the pressure gradient force and the Coriolis force. What we've seen up to this point was what the balance between pressure gradient force and Coriolis force equally balance in between the high and low pressures. The centripetal force comes into play when we're closer to the center of a high or low pressure system. When you get closer to a low, the pressure gradient force actually gets stronger. And since the pressure gradient force is stronger, there's going to be a net force pushing inward. What that net force does is it causes the air to turn. And so you get a circular motion, in this case counterclockwise around a low pressure. So let's take this example. We have a parcel down here at point 1. Pressure gradient force is pushing it high to low. But then the Coriolis force starts to turn it until you're at point 2. And at point 2, you have now become geostrophic. The pressure gradient force and the Coriolis force are fairly well balanced. But as it continues, it can't move in a straight line because these winds have to follow isobars. And so, since it's closer to a low pressure, that creates the centripetal force, causing it to curl counterclockwise around the low pressure system. Now, in the southern hemisphere, this would be backwards, because in the northern hemisphere, Coriolis force turns things to the right, like we saw down here. But in the southern hemisphere, the Coriolis force turns things to the left. So what we would have actually seen is, rather than a counterclockwise flow around a low, we would see a clockwise flow. Instead of talking about clockwise and counterclockwise, and then have to distinguish, well, that changes between the northern and southern hemisphere, we give it a general term of cyclonic flow. Cyclonic flow is the direction wind would travel around a low pressure. In the northern hemisphere, cyclonic would be counterclockwise. But in the southern hemisphere, cyclonic flow would be clockwise. Okay. Anticyclonic then would be the opposite direction. So let's take a look at anticyclonic flow. Well, what happens here is you still have a near balance between the pressure gradient force and the Coriolis force. But since you're really close to the high, what happens is that your pressure gradient force actually weakens. It becomes not quite as strong. So the Coriolis force actually wins out in this case, causing, again, a net inward force. That net inward force would then cause the winds to curl inward towards the high pressure, giving you your anticyclonic flow. Okay, so summary of the three forces so far. You get a wind, when you're looking at air aloft, a few kilometers off the ground, you get a gradient wind that flows parallel to your isobars, whether they're curved or not. If they are curved, then the gradient wind will flow cyclonically, in other words, the direction around a low pressure, which is counterclockwise in the northern hemisphere. But if the winds are going around a high pressure, they will flow anticyclonically, which would be clockwise in the northern hemisphere. Now, recall that the Coriolis force is weakest, and you could even say non-existent, near the equator. So what will happen here, the Coriolis force is zero. If not, it's practically zero. So the pressure gradient force wins there, and the winds will follow the pressure gradient force. Therefore, your centripetal force in this case would be roughly equal to your pressure gradient force. So here's what we get. The picture on the top left is a 500 millibar chart, and what we see are geostrophic winds. Winds traveling from high to low, but because of the Coriolis effect, they turn and they start following these isobars. Whenever you talk about winds aloft, you will always have winds flowing parallel to the isobars. But if you look at the figure on the bottom right, this is a surface map. And you have a low pressure, so the pressure gradient force goes into the low. And so winds are not following that because the Coriolis force. But from what we talked about, the Coriolis force should make these winds go parallel to the isobars. But if you look at these, the winds are actually crossing the isobars. Why? Why don't they follow this geostrophic pattern? The answer is the fourth force that we have not yet talked about. The fourth force is friction. The surface causes the winds to slow down, which causes the winds to turn even more inward towards the low pressure in this picture. First of all, how deep in the atmosphere can we account for friction? Well, the lowest part of the atmosphere that is affected by friction we call the friction layer, or the official term is the planetary boundary layer. And it reaches an altitude of about 1 kilometer. So the lowest 1 kilometer of the atmosphere is your planetary boundary layer. Now, because you have buildings, you have mountains, you have land and water bodies, you're going to have changes in wind patterns. Therefore, you're going to generate lots of irregular turbulent motion. And when you have turbulence, it's going to slow down the flow of wind. So since friction is slowing down the wind, the Coriolis force isn't as strong. Because remember, the Coriolis force gets stronger as the winds get faster. So as the winds slow down because of friction, Coriolis force weakens. As a result, the Coriolis force and pressure gradient force don't exactly balance. Pressure gradient force wins, and the winds will flow at roughly a 30-degree angle to the isobars. Now that's what's happening at the surface, but while that's happening, look here aloft. About 3 kilometers up, well outside of the planetary boundary layer, you're looking roughly 700 millibar level. You have a purely geostrophic wind because friction is not weakening the Coriolis force. So in summary, there are 4 basic forces that cause the air to accelerate. The initial push is the pressure gradient force. Without the pressure gradient force, there would be no wind. The second important force is the Coriolis force from the turning of the Earth. This determines the direction of the wind. And then you have the centripetal force, a balance between the pressure gradient and Coriolis forces. That's going to cause the wind to curve toward a low pressure system or away from a high pressure system, giving you the cyclonic or anticyclonic flow. And the fourth and final force is friction. That would be air drag near the surface. And as a result, you get geostrophic winds aloft, where the winds are perfectly parallel to the isobars, and at the surface, winds will cross the isobars at roughly a 30-degree angle due to friction. Around a low pressure system, they will be at a 30-degree angle moving in towards the low pressure, so you're spiraling inward. But a high pressure system, it would be 30 degrees outward. You're basically spiraling outward from the high pressure system.